Hello everyone. In this video, we will motivate the notion of linear regression, and we will formulate the problem, and we will motivate the notion of best fit line. So let us start this video. So this diagram we have seen in the introductory lecture also. Basically, there are two parts of supervised machine learning algorithms. One is a classification problem and one is a regression problem. So the main difference, and should I say the only difference between these two, is the output class label. In classification, output class is some categorical value, one of the class label, and in a regression, output is a real value. So let's see one example. It will become slightly more clear. So this classification example. So if we consider a problem of disease prediction, so given certain attribute or features of a person, we are supposed to identify whether the given person has certain disease or not. So for now, I am considering only three attributes: age, heart rate, and weight. So given these attributes, we need to classify them either, person having a disease and person not having a disease case. So it is a yes or no kind of classification problem. And since the output, which is the class value, which we usually denote with the abbreviation Y, is one of the categorical value, this problem becomes a classification problem. For a regression problem, we there is certain called one very frequently used regression problem is a housing price prediction problem. So given a certain attributes and certain features of a particular house, we are supposed to estimate its selling price. So for now, I'm considering three features only: area, bedroom, balcony, and using these three features or multiple features, it could be more than three features as well. We are supposed to estimate the selling price of the house. So since the final class value is real value, or you can say some non-negative real value, then the problem becomes a regression problem. Because the model should be outputting some real value. So that's why it has to be considered separately. Here, the model should output one of the class value, which is yes or no kind of output. So hopefully you all have studied up till this point in the introductory lecture. So let's in general see what is a paradigm of the machine learning algorithm and uh, what is its main function. So given certain input, machine learning algorithm should give certain output. It's very simple. So machine learning input will be usually given in terms of feature vector. Hopefully you are okay with this terminology. Uh, in the introductory class, it should be clear what is called as a feature vector. And output is either a class value or um, continuous value. So this machine learning algorithm could be seen as some mapping or some function who is taking an input as a feature vector, and it is outputting either a class value and a continuous value. So now we are going into the mathematical notations where this function which machine learning algorithm is learning is usually unknown function. If we know this function, then we don't need data. We don't need to train it. There is no such thing. But usually this function which machine learning algorithm is learning from a feature vector to final class value is unknown. So that's why this function from an input to output is unknown function, and it is being learned through a training data. So in case of housing price prediction, let this function be f. So if this function is f in housing price prediction, let the feature vector is of a dimension r to the d. So in housing price prediction, the final value is non-negative real value. So the function in the mathematical form could be represented as a f whose domain is r to the d, and it is ranging from non-negative real value. And in disease prediction, the function has a domain r to the d again, because we assume that every feature vector has a dimension d. and it is outputting one of the class label, either yes, that means person is having a disease, or no, that means person is not having a disease. Um, so in terms of linear regression, we assume a specific form of f which is linear. Now, this is a crucial assumption that we make. So let's see how it will look in terms of graph or in terms of diagram. So in x-axis, I'm denoting the input values. So first of all, let's say input is of a one dimension only. So it will be denoted by small x, and output is some real value again. So it will be denoted by y. So I want you to be comfortable with these terminologies: input, parameter, output. So in y equal to mx plus c, what is input, what is parameter, and what is output? So I would request you to comment what will be the input in this y is equal to mx plus c. Correct. X is the input, right? So x is the input. So let's specifically note this. Okay, tell me what is the feature in this particular y equal to mx plus c. Since input is of a one dimensional only, the feature is also x only. So input and feature both are the same thing in this case. If there are multiple dimensions of the input, we call the combined vector of consisting all feature values as the input. But in this case, only one feature is one dimension is there. So the input and feature are same. Okay, very good. Now, what is the output? Y is the output. M and C are parameters. And what machine learning algorithm is learning are parameters only. So since we have assumed a linear form of a function, it will have a this form. It will definitely have a this form. But machine learning algorithm will try to learn these MNC in such a way that given an input, it will give the specific output. So visually, you know the equation of the line, how the line looks like. So it will look a very nice. Ideally, in machine learning algorithm, we should learn some line which is passing almost all the points. So we'll come to this notion later. But the final output or a final model is a linear function, and visually it will be certain line only. Or if there are multiple dimension of the input, it will be certain hyperplane only. So if there are two dimension, it is certain plane, right? So if let's say the input is of a two dimensional, how it will look like? So input has a two features. Let me call it feature one and feature two, and both are being abbreviated as a small x1 and small x2. Now, what will be the what will be the linear function which is mapping these features to certain output y? So, y, it will output certain y, it will consider both these features. So, we need to assume certain parameter for the feature value small x1. So, you can assume m1 times small x1 plus m2 times small x2 plus c. Now, what are the parameters in this case? Y is output, small x1 is feature, small x2 is feature. Parameters are what? M1, M2, and C. That's correct. So these are the parameters. Why I'm specifically denoting is as in the back of the mind, you should be very clear. Machine learning algorithm will try to learn a certain parameter. The functional form will be fixed, and the machine learning algorithm will try to learn only these parameters such that given the input, it will give the some output. Okay. So hopefully these things are clear. The thing is, not all X and Y, that means not all inputs and output in the given data has a linear form. So in this case, hopefully it's visible. I have demonstrated few points using the orange color. I will slightly enlarge it. Now, if I ask you, learn some line which is giving certain input to output. So what input is where? Input is on an axis. So this is input and output is on a y. So learn certain line which is mapping input to the output. Again, through our abbreviation, input is only one feature and we will denote it with small x, and output we will denote it with small y. So can you learn some line which is passing through through these points demonstrated in this diagram? Since this relation with input and output does not seem a linear in this case. In this data, it is not linear. So even if we learn some function, it will look some weird function. It will look something like this. So this is highly non-linear function. And even if we are, okay to miss out few points, still we will not be able to obtain a fully linear line, which is passing almost all the data points. Hopefully it's clear that not all given input and output will have a linear relationship. And in linear regression, we assume that given input and output do have a linear relationship. So why this assumption makes sense and when this assumption will not make sense? So let's see few use cases demonstrating it. So this function assumption depends on nature of the problem that you consider. In some cases, making a linear assumption between input and output is okay. But while in other cases, making assumption of a linear function between input and output is not. So let's consider slightly MSQ kind of question, which will check your understanding, which is asking that which of the following problem has a linear relationship with input and output variable. So I'm giving you three options. One is a distance driven by a vehicle versus amount of fuel is consumed. Another thing is salary of the employee versus work experience. And the third point is population of the country versus number of years of the existence. So distance versus amount of fuel consumed. Can we assume that it has a linear relationship? Yes, because the concept of the average of a vehicle or it only demonstrate per liter how much distance it will cover. So this is obviously we can assume that it has a linear relationship. So this is correct. What about second? Salary of the employee versus work experience. So in most of the industry or in most of the working environments, there is a positive relationship between work experience and salary of the employee. It will in general make sense to consider it as a linearly related salary of the employee and work experience. As work experience grows, salary will grow. Clear, right? So what about say population of the country versus number of years of which it has come into the existence. So can you assume this problem will have a linear relationship? So actually it will not have a linear relationship. At certain point, let's say in certain generation, if you have certain amount of population, so that many marriages will be done. You can assume that it will be done in the country itself. So that many couples will be formed and they will have a certain reproduction rate, so certain number of childs. Now, as the population increases, the number of married couple will increase in a certain generation, and the number of child which will be having in the next generation will be also increased. So, in a linear relationship, uh, the change in output is constant with respect to change in the input. So all of this function you have seen, y equal to mx plus c, y equal to m1 x1 plus c, m2 x2 plus c. So if you differentiate it, you will get certain constant. So if you consider this function, dy by dx, if you do, you will get certain constant. It does not depend on the specific x that you are considering. It is m only. This is constant and this does not depend on x. If x is more, still it is constant. If x is less, still it is constant, which is n. But in this particular case, dy by dx depends on the current population. So it is not a linear relationship. And which function that has a dy by dx proportional to the input. So if you consider a hypothetical function which is e to the power x, now let's say y is equal to e to the power x. Y demonstrating the size of the population, x demonstrating the time from which the country is in existence. So this function, if you do dy by dx, what will it come? Again e to the x. So this depends on the input. So it is proportional to the current population. So it is not proportional to the input x, but it is proportional to the y. That means it is proportional to the current population. So actually, there are studies which are made which indicates that the population growth will have an exponential curve and it will look something like this. The use case, if you are given a population data versus the time from which the country came into the existence, it will have a data point like this. Hopefully, these data points are visible. I have drawn it through the orange color. And if you try to fit a line, you will not be able to fit the line very accurately all through this data. But if you try to fit certain exponential curve, you will be able to fit it. So one more thing before I go further, it need not have exactly this form. I took y equal to e to the x just to demonstrate that the derivation is proportional to the current y. It could be of the form y equal to some a to the power x also. Then also if you try to differentiate, dy by dx will be proportional to the current y. In every exponential form, dy by dx will be proportional to the current y. And I just, in this case, a will become your parameter, and that's what you will try to learn. Or you can assume y equal to some k times a to the power x. That is also valid assumption. You can assume y equal to k1 times a to the power k2 x. That is also valid assumption. So you can assume these forms as well. In this case, y equal to k1 times a to the power k2 x. Okay. Now, which are the parameters in this cases? I would request everybody to answer. What is the model we'll learn in if you assume this kind of functional form? I'll copy it and paste it in the new slide. So what are the parameters if you assume this kind of form? Input is what? First answer input. What is input? X, right? Bharat, input is X because that indicates the time from which country came into the existence. What is output? Y, exactly. And what are the parameters? Now the remaining are parameters, right? So K1, K2 and all are K2 and A, all are parameters, right? So whatever model or machine learning algorithm will learn only these parameters. Machine learning algorithm will learn this parameter such that it will fit your given training data. We will see the concept of fitting slightly later. Okay, so this is crucial assumption. Keep in the mind, we assume a linear form of a function. So let's try to demonstrate it using a few sequence of the question. How do we solve this linear regression problem? So consider this problem. There is person called as a John, who is having 200 or 2 lakh rupees signed in bonus, and then he is earning 4,000 every day. Now, X represents the number of days John has worked. Um, Write an equation representing amount of money John has earned in the thousands. So, please know, in this question, it is not explicitly mentioned it has a linear relationship. But because of this particular line that he earns rupees 4K every day, um, it should come into the mind that number of days it has worked and how much money he has earned, it will have a linear relationship only. So it will be very easy to see that if X represents a number of days John has worked, as X increases, the money the John is earning is increasing by 4,000 every day. And there is certain sign-in bonus that is in the on the day he is joining, it will receive certain amount of rupees, which is 2 lakh rupees. So the amount of money John has earned, if I denote it using the abbreviation small y, then the equation corresponding to it will become y equal to what will be the uh, multiplication value for small x. It will be 4 because as x increases, the money it will be receiving will increase by 4. So it is 4 times x. plus no matter what how many days he has worked, it will have some amount of sign-in bonus as well. So it will be 4x plus 200. But the problem in this case is you are given certain description of problem. More specifically, there is explicit mention of a relationship between number of days the John has worked. What is the signing bonus? And that is explicitly mentioned in the question itself. So you are able to obtain this relationship very nicely, and you did not face any problem. But let's say um, instead of giving this relationship in the question itself, if you are given certain tabular data, and in this data, the similar problem has been formulated. There is person called as a John, and he's earning certain amount of money. You have to, I mean, in the question, it is explicitly mentioned that we should assume that the number of days it has worked is linearly related with the amount he has earned. So if you are given certain data, how you will be able to solve it through the table. And in this table, let's first clarify what is the input. Number of days is the input X, and the amount earned is in output Y. So hopefully these abbreviations are clear to everybody. Now I would request you, everybody, to answer how to find linear relationship between X and Y using this data that you have been given. Plot. That is one answer. Okay. Uh, that's a valid answer, but it will become cumbersome because 228 is where in the plot. You will, even if you try to plot it the y-axis, it will go out of this particular um, region or out of this particular slide. So this is correct, but that's not feasible. The hint is saying that something you already learned as a linear algebra. Can you formulate this in some way? Take a first entry. Please note that we have assumed certain this first column as the input, which is small x, and the final output variable as small y. Now you take a first entry and you assume certain relationship first. That is the first task. So what is the relationship? Y equal to mx plus c. So what is again, you should know that what is input output that in the table I already mentioned. But what are the parameters? Parameters are M and C. That is what you should estimate and you should find it. So how to calculate it? As Rohan has mentioned, take a first entry and formulate certain equation. So from a first entry, if the X is 7, then Y is 228. So from first entry, Y equal to 7M plus C. And you can form a similar equation, which is a second equation from a second entry. Let's replace the value of Y as well, because that is in the table we are given. So X is 7 and Y is 228. Similarly, when X is 14, Y is 256. So up till now, is there any confusion? This is some linear equation that we have formed. That's all we have done. Is there any confusion? Now the next step is to solve this particular equation. How do we solve it? Elimination method. Yes, exactly. Samir is saying elimination method. If you try to do this problem in the Gaussian matrix form, then you can do a Gaussian elimination as well. That is a standard terminology in the linear algebra that you have studied. So let's simply do the elimination. It's very simple problem. So what is the thing? How to do elimination? I will tell first thing is to subtract first equation from a second equation. So if I do that, what I will get? 7m equal to 28. So m will be 4. Is this clear? Yes. and just replace a value of m in the first equation. I will number the equation so that it is clear what equation I am referring. So if I replace m into the first equation, what I will get? C is how much? 200. So this is a small elimination method. Everybody should be aware of it. It is class 12 technique. And as some students are mentioning, you can do some kind of Gaussian elimination as well. So you can represent this data in the matrix form and create vector x as the input vector and vector y as the output vector and form a system of linear equation, and you can solve it. Okay, so we got the same equation. Please know what is the equation we obtained? Y equal to 4x plus 200. Earlier, we obtained it using a description in the problem. Now we have obtained it through the data. Some data points that we have obtained it. The next step is this feasible in every cases? So there is a problem if we can try to apply the same method, that is a substitution or Gaussian elimination method, every time. The problem is it assumes that the input is exactly linearly related with the output. That means when we form a system of linear equation, it has to be exactly equal. If there is not, there is no concept of approximately equal in that. So if we have a data points like this, so it looks almost linear data point, but still, if you try to form a linear equation and solve it, you will not be able to solve it. Can you obtain a line passing through all these points? Are all these points are linear, everybody? They're not linear, right? Obviously not linear. Through the look of it, it's not linear. Fine. But, can I assume a linear relationship between input and output in this case? You can assume it, right? Even though they are not linear, they are almost linear. So you can assume a linear relationship. So if you try to apply a substitution or Gaussian elimination, you will be clueless because they are not linear, and if you form a system of linear equation, it will not have any solution. But still, we say that input have a linear relationship with the output or almost linear relationship with the output. So in this kind of cases, we will be left clueless if we try to rely on the substitution and the Gaussian elimination alone. Another thing is there might be some error and noise while recording a data point. So even these are exactly linear, exactly input is linearly related with the output. There is some linear function relating to it. There might be some noise in calculating y. So you can assume that this was in this particular diagram, this was the actual y. But while the recording, it came to this. It might happen. There could be some noise in the recording a data point. So in that case, even if x and y are linear, if you form a system of linear, if the actual function is linear, still, if you form a system of linear equation, it will not have a exact solution. So both of these problems are clear to you. What is the problem if we try to keep applying substitution and Gaussian elimination? So we have to come up with something else. So let me try to point a few more data points and try to demonstrate what exactly we want, and it will be more articulated. So we want something called as a best fit line or a best fit linear function, which is passing almost all data points, or which is almost estimating all data points. So let me draw one line, which is through orange color, not orange, but let's say blue color, which is this line. So it is not passing through all points, but few points it is passing. Let me draw another line, which is of pink color, which is very deviated, and there is another green color line. So which line is best according to you? If you learn this blue line, it is better than learning the pink line and the green line, obviously, right?
So how to exactly articulate this, that this blue line is better in the mathematical form? You need some mathematical notation. Okay, every time you are not going to plot this data, you are not trying to draw approximately blue line. Okay, somebody will come that, okay, this blue line, I will come with some other line. Then this is other line with, let's say, so if blue, now tell me whether blue is better or red is better. So you need some formulation. Okay, visually somebody is saying blue is better. Somebody will argue that red is also better. So there is some formulation, some mathematical formulation or some quantifiable formulation we need for this baseline argument or base fit line argument, and that's what we are going to do next. So as one of the student has mentioned, what we are interested in is something called as a line which has a least deviation from estimated data points to this actual data point. So if I try to articulate deviation by this gray color distance every point, so at this point the distance is very small. At this point is also small. At this point is also small. But for other points, the distance is slightly this. Similarly, for these points, the deviations are this. So if we try to mathematically quantify, we want a line which has a least deviation in sum for all the data points. So let's try to mathematically quantify these arguments.
So we will end this video here, and in next video we will mathematically formulate the notion of loss function, and we will see how we can solve the linear regression problem. So thank you very much for watching the video. We will meet you in the next video.